In this presentation, we're going to talk about the ways in which variables can be measured, the different levels of measurement, designing measures that improve the validity and reliability of your research, and how to construct research instruments for data collection. I will also tell you that this is one of my favorite chapters in the book. I really like to talk about measurement. That may be a bit unusual, but I hope I can impart some of my enthusiasm for this topic to each of you. What is measurement? Measurement in this context is really a way to operationalize your research variables or your research concepts so that you can measure them. And in order to do that, we must understand these concepts and constructs and break them down into different dimensions and indicators. I apologize that this graphic is difficult to see, but I want you to see how difficult it can be to take a construct like healthcare quality and operationalize it into measurable terms. And it really depends on what dimension of healthcare quality you want to measure and how you want to go about doing that. And as you can see from this graph, there are different dimensions, and under each dimension is an indicator that may help in measuring the construct. For example, one dimension of healthcare quality is the structure, and an indicator to measure that might be the certification of professional staff, the condition of medical equipment, or the technology available. So that's one indicator that might be used to measure one dimension of healthcare quality. You can see there are several dimensions. Most of the time, it's advisable to use existing measures in the field in order to measure your variables if they exist. And the reason to do that, actually there are several reasons. One is it will save you time and money. Two is if you do a search of the literature and you see that these instruments have been used, they have published reliability and validity statistics so that you know you're using a reputable instrument that has good measurement statistics. It validates your research. So when possible, it's always advisable to use established measurements. This next section deals with levels of measurement, and I cannot tell you how important this is in terms of being able to look at your variables, operationalize them in measurable terms, and know what level of measurement each variable is. Because the way you measure your variables dictates the type of statistical analysis that you can use to analyze your data. There are some statistical methods that are only used for nominal or ordinal variables, and others that are only used for interval or ratio variables. And we'll talk about that on the chapter on statistical analysis. My helpful hint for this week is that you should also review the lecture material on levels of measurement. Many of your activities or assignments for this week will revolve around these lecture materials and focusing on validity, reliability, and levels of measurement. Having said that, let's talk about the nominal level of measurement. Nominal levels of measurement categorize objects, individuals, or events into different groups or categories that are mutually exclusive. Some examples are sex, ethnicity, place of birth. Nominal variables don't have measurement meaning. They're categorical in nature. They just divide data into categories. Ordinal levels of measurement rank order individuals or objects or events, could be anything. But for example, using an ordinal scale, we might rank all people in our classroom from tallest to shortest, and we can line everyone up from tallest to shortest. However, we would not know how much taller the person ranked number 1 is than the person ranked number 2. So although it puts them in an order, there's not a defined space between each of those items, individuals, or events. The example here is satisfaction with physician services. Might be very satisfied, somewhat satisfied, not satisfied, but we don't know the distance between those categories. Interval levels of measurement have the characteristic of rank that we see in the ordinal scales, but they also measure the distance between different points on the scale. So the typical example you'll see everywhere is temperature. Because when you're looking at a thermometer, the difference between 100 degrees and 80 degrees is 20 degrees, which is the same difference between 50 degrees and 30 degrees. So it's a set distance between points. However, in interval levels of measurement, there is not a true zero, meaning the absence of an entity. Again, using temperature as an example, a 0 degree temperature does not represent an absence of temperature, so it's not a true zero. Ratio scales are the most sophisticated or the highest level of measurement because they have the ability not only to rank individuals, objects, or events, and there's also a known distance between the different rankings, but they have a true value of 0. 0 is representative of the absence of whatever it is that you're measuring, whether it's height or weight. It is a true 0. One of the goals that we have as researchers is to try and minimize errors in measurement. Errors refers to the source of observed differences in the study elements that are not due to true differences in the elements themselves. It's really just a fancy way of saying that measurement errors are reflective of the difference in what you measure as compared to the true value in the population. There are two types of errors that can occur in measurement. One is a systematic error and one is a random error. Of the two, a systematic error is probably the more serious. One happens by chance and one is a problem. The one that happens by chance is a random error. Systematic error indicates there's some problem in the process or the manner in which you decided to measure your variables. It might be that it's not operationalized properly, there aren't enough different ways that you're measuring your concept. It might be that there's something about the researcher or the way the questions are asked that bias the results, but it's a systematic problem as opposed to a random error when the characteristics of the investigator or the respondents influence the measurement process. Maybe you're tired, you've been asking questions all day, you may ask the question in a different way. Maybe the responder is tired, has lost interest, is hungry. So it's more a fluctuating issue or a random error as opposed to something wrong with the process that you're using. Validity and reliability in measurement is very specific to the task at hand. A valid measure has categories or responses that are reflective of all the important aspects of the concept under study. So if you were going to measure something like hope or faith, which is a little more abstract, you would want to measure all of the indicators of the factors that make up hope or faith. Reliability, on the other hand, is really looking at consistency of measurement over time. Do you get the same results repeatedly when you use the instrument? There are many different types of reliability and validity in measurement, and we're going to start by talking about different types of validity. The first type of validity is face validity, and it's really just what it says. On superficial inspection, does an instrument appear to measure what it's supposed to measure? For example, does the test on statistics include numbers and calculations? So it's really just on the face of it, does it appear to be valid? Construct validity is a little bit more difficult because you're measuring a construct that has many dimensions and may be more abstract. So you have to use agreed upon criteria or established measures from the literature. It can also be verified by factor analysis, which is a process that will look at, do your indicators measure the constructs for which they are intended. Let me give you an example. If you want to measure, let's say, depression, then we might want to look at construct validity in terms of instruments that assess energy level, flat affect, loss of appetite, sexual desire, isolation. We would want an instrument that would look at these factors which make up the construct of depression. In content validity, you're looking at, do the response categories in the measurement really represent the dimensions of the concept? For example, if you want to look at the highest level of education completed, then responses should include an accurate listing of all possible categories, from high school to graduate degree. So you want your content to be reflective of what it is that you're measuring. Concurrent validity is a way to compare the investigator's measurement instrument with a similar instrument that's been tried or has been recorded in the literature as being valid. So if you are developing a new test on intelligence, you might give it to a subject and in addition give them the standard IQ test. And the results should be related or consistent with one another if your new instrument has concurrent validity. I think one of the best examples of predictive validity is that high school grades are very predictive of success in college. So what we can look at is, do people who make good grades in high school also make good grades in college? If we find that that is indeed true, then how we're measuring that would have predictive validity. Now let's talk a little bit about reliability. Remember, reliability in measurement is getting consistent results time and again when you're using an instrument. There are many ways to test reliability, and we're going to talk about each of these. Test, retest reliability can be used to assess an instrument at two different points in time. So let's say we want to know the reliability of a new exam on research methods. We test students at the end of a semester and at the beginning of the next semester, so there's a time lag. The test should produce more or less the same results. Okay? And that would be test, retest reliability, using the instrument to test at two different points in time, and the results should be highly correlated. You can also use parallel forms of an instrument or split the instrument in half and administer one half to one group of people and the other half to the other group of people, and then calculate a reliability coefficient to measure the relationship between the two. And we'll talk more about a reliability coefficient in just a minute. We can measure the internal consistency, which is a reliability measure, by comparing two quantitative scores, as in the last example. And what this does is measures the degree of relationship between the two scores, or how highly correlated the two scores are with one another. Typically, this is known as a Cronbach's alpha. That's the statistics that's used. It ranges from 0 to 1. Of course, the closer to 1, the more perfect the correlation between the two. Generally, in research, measurement of 0.80 is the acceptable level. So you want anything that's correlated 0.80 or higher. And then there is inter-rater reliability. And I always think the best example of this is at the Olympics. When in ice skating, you have the judges who hold up the numbers. Inter-rater reliability would mean that that panel of judges have very similar scores with one another after viewing a performance. That would be inter-rater reliability. There are several steps that we can take to improve the validity and reliability of measurement in our work. We can use existing measures that have published data on reliability and validity statistics. We can ensure that people who participate in studies know that the information is confidential so that they will give truthful answers. We need to be really careful with how we select our instruments